Okay, nice to meet you all. I'm Stefano Giarratana. I'm a PhD student at the University of Bologna, and today I'm going to talk about radio afterglows of gamma ray bursts. I think you have seen most of it during the few talks, but due to a strong jet lag, I'm not going to change it, so I'm sorry for that. But first of all, what are gamma ray bursts? They are the most powerful explosions in the universe, except for the Big Bang, luckily for us. And they are usually divided into long and short GRBs according to their duration. Long GRBs are longer than 2 seconds. They have an average redshift of 2. They are found predominantly in high star forming regions, and they are associated with supernovae. On the other hand, short GRBs are shorter than 2 seconds. They are closer, and they are found in all morphological types of galaxies, and they were recently associated with kilonovae, which are a sort of supernova for merger events. For that, we think that long GRBs are due to the collapse of a single massive star, such as a Wolf-Rayet star, while short GRBs are due to the merger of 2 neutron stars or a neutron star and black hole. And regardless of the progenitor channel, a highly magnetized neutron star or a black hole will eventually be produced. And in the standard model, the central engine will launch 2 relativistic jets. Always in the standard model, multiple shells are ejected, and when a faster shell catches up with the slower one, here, inner shocks arise, the electrons are accelerated, and they produce very high energy, gamma rays through synchrotron emission. The outflow continues to expand until it reaches the surrounding medium and interacts with it through external shocks, producing the so-called afterglow emission that can be seen from very high energy down to the radio band. And what I'm doing here, not here, in Bologna, is studying GRBs in radio, but why? First of all, because as we have already seen, actually, with radio we can discern between different components within, different emitting components, as we will see later on in this talk. Then with high resolution, we can estimate the viewing angle, so that the angle at which we are observing the jet. We can estimate the collimation angle, so that the angle at which, within which the jet is launched. And then we can constrain the size and the structure of the jet. And finally, we can have some hints about the progenitor by studying the circum-burst medium and the host galaxy. Regarding high-resolution studies of GRBs, which is what I'm interested in, actually, there are 2 types of things that we can do. The first one is, if you are looking directly towards the center of the jet, we can see the superluminal expansion. Or if you are looking slightly off-axis, as here, we can see the displacement of the center as an apparent proper motion. And the first masterpiece in the first case was by Taylor and collaborators. And as you can see here, the angular size as a function of time, we have some, they had actually, some upper limits with the VLBA. Then they had 2 detections here at around 20 days, 30 days. And then another detection here at around 80 days post-burst. And since the angular size of the GRB is increased, this was the first proof ever that GRBs are superluminal expanding. On the other hand, regarding the displacement, this was the other masterpiece by Taylor and collaborators, and then also by Giarratana and collaborators the year after. You can see here the 2 VLBA observation, and here you have the first epoch, and on the left, the second epoch, and there is a displacement of a few mass. Now I'm going to give you 2 examples of studies of radio GRBs, let's say, and I will tell you why we have only 2 VLBI papers in 20 years. So the first one is 2010 15A. This was an interesting burst because it was detected at very high energy by the MAGIC telescopes. And if confirmed, this would be, I think, the 5th one or the 6th one, over like more than 1,000 GRBs. So it's special. And for this GRB, I'm showing you the flux density as a function of time. We call it light curves. And for this burst, we had VLA, E Merlin, and EVN and D Merlin observation at 5 GHz in blue and at 1.5 GHz in gold, orange. And we also gathered optical observations here in green, purple, and red, and also the Swift XRT light curve here. The light curves you can see here are the modeling light curves we are using to model the emission, which is a single forward shock model in this case. And the main thing here is that this model is heavily dependent on the surrounding medium profile. We usually take it to be a homogeneous surrounding medium or to have a wind-like profile. And in this case, if we don't include the radio, but we use only optical and X-rays, we can say, well, we cannot rule out one of the model. We can say that the homogeneous medium is more likely, but we cannot rule out the wind-like profile. While when we include the radio data, we can totally break the degeneracy in the afterglow modeling because the wind-like profile is completely ruled out. And since we had also VLBI observation, what we try to see is an expansion or a displacement in this case. But if we take the expansion observed for 03, 03, 29A, or the displacement of 1708, 17A, and we put these effects at redshift of our burst, which is 0.426, we would have seen these effects with an angular resolution better than 0.09 mass, which is feasible for VLBI, but only for high signal-to-noise ratio detections. And unfortunately for us, our best signal-to-noise ratio was 7. So we could put only constraints on the displacement and on the size of this GRB. The second one is the brightest of all time, the boat. And this is quite interesting, as usually for an interesting GRB, there are like 5, 6 papers. And for these that happened in October last year, there are already 62 papers on the archive. And I'm telling you why. First, because there is a TEV emission, and this was the first GRB ever detected in this band. Then, because this burst was so bright and close by that it partially ionized the ionosphere, so it increases the electron content in the ionosphere, which is quite scary, I would say. And finally, because the X-ray emission was so bright again that it was reflected by dust in our galaxy, producing these beautiful rings, and there is a movie online with these rings that are expanding. And since this burst was very, very interesting, many groups tried to look at it and try to model the emission. And the first one was the group by Ren and collaborators, where they said, okay, this is a top hat jet in a wind-like environment. A top hat jet is a perfect cone. And as you can see here, they can reproduce the data very well with their light curves, but they don't have early and late time radio data. And in fact, when we include some radio data, as you can see here, for the second group, which is by Saturn collaborators, there is here the light curves in radio. They can reproduce all the bands, but radio is not perfectly matched. Then came Laska with this beautiful data set, because from JEV to radio. And here I'm showing you not the light curves, but the SED, so the flux density is a function of frequency. They tried a lot of things, but I'm only using this because it's the most representative to me, at least. And they can reproduce the X-rays, the optical, and the near infrared, but the radio cannot be reproduced at all. Actually, they can reproduce it only if they assume that the synchrotron emission is evolving in a non-standard way, so it means new physics. And finally, there was this paper by O'Connor and collaborators in which they say that there is a structure jet in a medium which is not a homogeneous, well, it's almost a homogeneous one. And they can reproduce all their data, but as you can see, they have only a few data points in radio. So the main point here is that to cite the notorious BIG, more radio, more problems. Also, well, if we consider all the models there are on archive, we cannot reproduce in any way our observation with AMI, which is a compact array in the UK, working at 15 gigahertz. And this is the light curve we had from 3 hours post-burst And these time beams are 15 minutes time beams, which is incredible for a GRB. And we have this beautiful pic here, and this cannot be reproduced with any model. And we also had VLBI observation with EVN, which is an array comprising antennas in Europe, South Africa, and Asia. And we had 5 epochs. The first one was 6 days post-burst, and it was a total mess. We cannot use it because they did some crap with bad cablings. Then we had 2 beautiful detections at 8 and 5 gigahertz here. And then we have other 2 observations at 100 days, but I'm not showing them to you because my supervisor doesn't want to. Well, we are still fixing some calibration, and we are searching for an expansion or a displacement of the GRB. So what can SKA and ngVLA do for GRBs? I think you all know what they are, so I'm going to skip it. And I want you to focus on the bottom panel here, on the upper panel here, where you can see the flux density, the peak flux density as a function of time. The peak flux density is the maximum flux density at which we can see the GRB. At 8.5, I think, yeah, gigahertz, yes. The red dots are the detection by Chandra and Frey in 2012. The triangles are the upper limits, so thank you, Chandra, for the data. And the gray dots are simulated population of GRBs by Giarratana and collaborators in 2013. As you can see, this is the sensitivity of MeerKAT when it will be included in SKA, so that's working in this band. And we should pass from 30 to almost 100% of detection rate. So whatever we look at, we should detect it, which is incredible, at least at the peak time. And we should pass from less than 50 to almost 50% of detection rate at the transition time, which is the time at which the burst becomes non-relativistic. And this is important because in this phase, the GRB can be described with a set of equations that are independent from the relativistic phase, so we have an independent way to estimate the energetics. And this, in fact, is the flux density as a function of time, the flux density at the transition time. And with all these beautiful data, we can improve the cosmological relations, such as the Amati relation, that are heavily dependent on cosmological parameters. So we can have an independent way to estimate these parameters. And finally, what I'm interested in mostly, which is not cosmology, nothing is cosmology, but it's not my thing, is combining these super sensitive arrays with VLBI to study, not only to see every GRB, but to study the structure and the geometry of them. So to conclude, radio is really important to break the degeneracy in the afterglow modeling, as you have seen for 2010-15A, to reveal emitting components and mechanisms, such as in 221009A, and with VLBI to study the size and the geometry of the afterglow. And with ngVLA and SKA, we will do it for every GRB. Thank you.
Do we have some questions for Stefano? Okay, could you go back a little bit to the sensitivity plots?
Yep.
Okay, so I'm just trying to read that there. That looks like it's 0.1 microjanskis is what you're looking at?
Yep.
Okay, so that, I think, use the mic. Oh, sorry. Okay, so the sensitivity limits you're putting down there are 0.1 microjanskis. So you wouldn't be able to image those with the long baselines in reasonable exposure times, would you?
Actually, I don't think so.
Yeah,
but...
okay, so yeah, that's for detection, right?
Yeah. Okay.
So do you have a sense of what fraction of the GRBs you'd actually be able to do VLBI imaging on?
Okay, that's a nasty question, actually. Okay. I mean, usually you can do it only for very close by GRBs because the expansion is of the order of usually a few mass if you are really, really lucky. And GRBs are cosmological. So, so far, I think you can do it only for GRBs that are of below 0.2 redshift. Okay. So really, really close by. At maximum 0.4, we have tried, but
Okay, so I mean, yeah, ngVLA, it may get better, right? Because you'll have good sensitivity at much higher frequencies than
that's true
now.
That's true, but this is only for, I mean, what I've put in here is for a frequency of 8.5. So I haven't checked it for high frequencies.
Okay.
But yeah, it's a good point.
To look at that at 40. Because if you go above 40, then you run into weather issues. But yeah. Okay. All right.
Maybe just a follow-up comment on that is that the nearby ones, of course, have the highest odds of then also being gravitational wave sources. So it's not all bad. What are your thoughts?
I agree. I totally agree. Yeah, indeed. But this is mostly for long GRBs. These are all long GRBs. So yeah, if you're interested in short GRBs, I suggest you that that poster there. But yeah.
Okay. Do we have another question? All right, if not, let's thank Stefano.